and we're so glad to have you in attendance today. Our speaker today is Dr. Alex Miller, now Professor Alex Miller of Sonoma State University. She is also a veteran of the CSU system in an existing capacity and one of its alumni. She received her undergraduate degree from CSU at Sonoma State. So much like herself, she's had a start in the CSU, went on to receive her PhD from UC Santa Barbara as an NSF graduate during her time there, before taking up an appointment at Wellesley College and then joining us here at faculty. The topic today is complicated. So I shall leave the introduction or the material itself to our very own Professor Alex Miller. Thank you very much.
Thank you, everyone, for coming. This is such a great showing for this series. So before talking about my talk, I thought I would say a little bit more about myself. So indeed, I also started at Cal State, and I sort of had an interesting trajectory through my academic career. So actually, I spent most of my life doing theater. So actually, with these lights here, I feel quite at home. I feel like I'm back on the stage. And really didn't come to science, come to physics until later in life. So I started college at SF State as a theater major, and then just took physics because it was a GE requirement, and just loved it and never turned back. And even when I entered physics, I started by doing experimental work, and then it wasn't until I got to grad school that I switched to theoretical quantum gravity, which is my field of research. So anyways, I really wanted to tell you all about that because I know many of you in the room are physics majors, but many of you who I know from my Phys 100 class are not physics majors. But it's never too late to join us in studying physics. So today I'm not going to talk too much about my research, which again is in the field of quantum gravity. I decided to go a slightly different route. So this talk is the What Physicists Do series. And I'm a theoretical physicist. And I don't think we ever had a theoretical physicist yet this semester. I don't know. Do you know when the last theorist spoke? What? Here?
Oh, in the spring there would have been.
Okay. But not this semester, so I'm the first one since I've been here. And so I decided really to focus on sort of what it means to be a theorist and what theoretical physicists do. And in modern times, really, theoretical physicists, not just in the field of quantum gravity, but in condensed matter physics and particle physics, we often put symmetry at the forefront. We really treat symmetry as the starting point and then derive everything from symmetry. And so in this talk, I'm sort of going to do a survey of symmetry, starting from sort of Noether at the beginning of the 1900s, and Einstein actually, and talking about developments all the way up until thinking about things like the Higgs boson, which maybe some of you remember the Higgs boson wasn't discovered that long ago. And so really symmetry is necessary to understand all of these things and everything in between. So if you don't know about Noether or the Higgs, you could have just titled my talk on symmetry, it's important. Because really, if there's one thing you take away from my talk today, it's just that symmetry is quite important. So, people have always been drawn to symmetry, right? We have some natural inclination to like things that are symmetric, right? So if we go back in time and think about Ptolemy's picture of what he thought the universe looked like, of course, Earth was at the center of the universe. And because of this natural inclination for symmetry, well, I don't know what Ptolemy was thinking exactly, right? But he wanted everything to move in perfect circles. So he imagined the Earth and then objects orbiting the Earth in perfect circles. Now that didn't match the data, and so he decided instead these bodies would move sort of in little circles as they move in circles, and that fit the data a little bit better. Of course, we know this is not the correct picture of the universe. But he because of this desire for things to be symmetric, he applied that to his science. Now we learned that this is wrong, right? Objects, now we have the better picture of our universe, where the Earth is not at the center of the universe, but we still have objects orbiting the sun, right? For instance, in our solar system. But we know those don't move in perfect circles either, right? They're sort of elliptical. But we might want to approximate those ellipses as circles. They're pretty close. And the reason we would want to do that is because there's a lot of utility in symmetry. So you start to see this from your very first physics class that you took. So in physics 114, so who's taken 114 so far, or is in it right now? Right, so a lot of people have taken 114. So you probably learned about Newtonian gravity. And there you learned that we have this formula for the gravitational field, from which we can get the force of gravity for point masses. And so that's pretty easy. But if you have more complicated shaped objects, then you would have to do a much more complicated formula. But if we have these objects that are spherically symmetric, now this could be a hollow sphere or a solid sphere, it turns out that this is mathematically identical to the gravitational field around a point mass. And so that makes our lives easier, and we want our lives to be easy, right? And happily, a lot of bodies that we want to study, like the planet Earth, is approximately a sphere. But is the Earth a perfect sphere? No, it's not a perfect sphere, right? So this is a nice approximation that we might want to use, but it's not really so fundamental, right? This doesn't feel fundamental. It feels just like, well, some objects out there that we like to study happen to be approximately spherical, and if we make that approximation, our lives become easier. And like the classic joke is that a physicist will approximate a cow as a sphere to make the math easier, right? So this is why we like symmetries. And then maybe for those of you who have taken 214 so far, you learned about Gauss's law. Right, and here again we learned that there was a lot of utility in symmetry. So studying the electric field around a point charge is pretty easy. And then we studied a lot of other distributions, like a line of charge and a sheet of charge, an infinite sheet of charge often. But do you ever actually have an infinite sheet of charge? No, right? If you're very close to a sheet of charge, you can treat it as infinite. You never actually have one of those. And a line of charge, again, we would treat this line of charge as though it has some continuous distribution of charge. But again, this is really just an approximation. If we have a wire with some charge along it, right, what actually, if we have a charged wire, what is it about the wire that makes it charged? Anyone? Like generally a charged wire, what has to be on the wire in order for it to be charged? Electrons, right? So you probably have some excess, if it's a negatively charged wire, you have extra electrons. Right? And these are really points along the wire. So you have some wire maybe, and you have a bunch of extra electrons. But this is a continuous distribution of charge. So when you apply Gauss's law, and we treat it as though you have this continuous distribution of charge, again, that's another approximation. But it makes the math a lot easier, and so we like it. Still, this is not really fundamental. Now this is feeling like there are certain things that happen to be symmetric, and if we approximate them as perfectly symmetric, that's easy, but it's not very fundamental. And really, since the days of Newton up until the beginning of the 20th century, this is how we thought about symmetry, as being helpful, but not fundamental. Now that all changed at the beginning of the 20th century, especially with Noether and of course Albert Einstein, because right, he shows up everywhere. With starting really with their works, today we really think of symmetry as the foundation upon which theoretical physics is built. Right, so today, I as a theoretical physicist don't think of it as something that can just be useful in approximating things. What we'll see in my talk today, and again, this is really there's a big takeaway from my talk, this is it. It's that I really think about symmetry as the starting point. If I'm defining my system, I start by defining its symmetries, and then derive dynamics of the system from those symmetries. All right, so the outline of my talk. So first we have to make sure we're on the same page. When I say symmetry, what do I mean by symmetry? And really, I can mean a lot of different things. So we're going to talk about the different types of things I can mean when I say the word symmetry. Then we'll sort of go through the different fields of physics. We'll start by thinking about special relativity. Now, what did Einstein do, right? Einstein developed special relativity. What did he do that brought symmetry to the forefront? Then we'll move on to thinking about classical mechanics. This is where Noether connected symmetry to classical mechanics. And then finally, we'll talk about quantum mechanics and how does symmetry play a role there. And we'll learn that, for instance, enforcing symmetries in quantum mechanics does things like help us actually discover new types of particles. So we really can gain a lot from symmetries in quantum mechanics. And then finally, depending on our timing, I'll talk about some advanced topics in symmetry. And this is really getting into more modern research. All right, so what is symmetry? So totally generically, I would say if after performing a transformation on an object, one finds that nothing has changed, then that transformation is said to be a symmetry of that object. So whenever you define a symmetry, you have to think about two things, really. You have to think about what is the object you're talking about, and what is the transformation you're going to perform. And this might sound vague to you, but it's sort of purposefully vague. It's really that this is general, because as I said, lots of different things can be symmetries. We can talk about lots of different types of objects and different types of transformations. So let's start by talking about what probably are the most familiar types of symmetries, which are just geometric symmetries. Right, so if we have a sphere, so for instance, I brought a sphere right here, right, and we rotate it a little bit. If I show you the sphere and I rotate it, if you look back at it, if this were a perfect sphere, you would not be able to tell that anything has happened. So my object is a sphere, my transformation is a rotation. It looks like nothing has happened, and so I would say that this is a symmetry of my sphere. So a sphere is symmetric under rotations, which hopefully is pretty clear to my students. On the other hand, I could consider a cube. So again, I have a cube here, which is kind of small, sorry. We can imagine also, so a cube also feels pretty symmetric. Right? A sphere feels very symmetric, a cube feels symmetric. If I rotate a cube by just a little bit, this cube looks different, right? This, you know that I did something, right, to this cube if I rotate it by just a small amount. So this rotation of a cube is not a symmetry of it. But if I rotate it a full 90 degrees, oh, now I'm back to a place where it looks like nothing has happened. Right? So only if I rotate the cube by an integer number of 90-degree rotations, right? So this is a 90-degree rotation. I could do it an integer number of times, so I could keep rotating it by 90 degrees. Those are all symmetry transformations of my cube. So here we see two of our primary classifications of symmetry. So we can talk about continuous symmetries and discrete symmetries. So a sphere, because I can rotate it by just a tiny little bit, or a whole lot, and it doesn't matter, any of those are a symmetry. That's why I would say a sphere is symmetric under a continuous set of rotations. I can do any amount of rotation I want, and that's a symmetry. Whereas a cube is only symmetric under a discrete set of rotations, because I have to do it by a full 90 degrees, right? So we'll see this distinction between different types of symmetries is going to come up later in the talk, so keep this guy in the back of your mind that we have sort of these continuous and discrete symmetries. So the next type of symmetry that you've probably learned about are of functions, right? So you probably, maybe in high school, right, even learned about symmetries of different functions. So you could have, for instance, an even function, right? Remember, even functions are when you flip this, right? You send x to minus x, it looks the same. So now our object is this function. Our transformation is sending x to minus x. It's flipping the graph, right? And we say it's a symmetry because we flip it and it looks like nothing has happened. An odd function, right? So again, our object now is this function. Now our transformation, if we just sent x to minus x for an odd function, it would look different, right? If we flipped this function, it wouldn't look the same. So that is not a symmetry of this function. But it is symmetric under flipping it and then adding a minus sign out in front. So sometimes your transformations can really require a couple different steps. And then those steps together form a symmetry of. So you can imagine this guy, you would have to flip it and then flip it across the x-axis also. But then that would be a symmetry of this function. And then we could consider things like periodic functions, which you can imagine shifting this whole graph over by a certain amount. And again, these are all said to be discrete symmetries, right? Because if you shifted this guy by just a little bit, it would look different. But if you shift it by a full wavelength, then it would look the same again. So hopefully these are pretty similar, or pretty familiar types of symmetries to all of you. But this is a physics talk, right? We've been talking a bunch of math, really. What about symmetries of physical solutions? Right, so what do we do in physics, right? We want to study, for instance, the paths of particles. We want to solve for, we toss a ball, you have some projectile motion, we throw it, we want to solve for the path of that particle, which we can describe by a function. So we want to see if these solutions, if the path of that particle, for instance, does it have any symmetries? And so for those of you who have studied, for instance, waves so far, so waves, and this could be a sound wave, this could be a light wave, this could be an ocean wave, right? So if we have a wave, a periodic wave, it can be described by a sine or a cosine function, right? If we have a periodic wave. And just like the function that we just saw, right? Just like how this function has a discrete symmetry, this wave, I would say, now has this symmetry because it's described by that same function, right? So you can imagine, again, shifting this whole function over by one wavelength, nothing would happen. And so if we want to quantify this a little bit, right, our solution to our wave equation is some cosine function. And what we're going to do is we're going to apply a transformation. So our object is this function, which describes our wave. Our transformation is sending x to x plus some amount. So that's shifting our graph, right? By adding something to x, that's just shifting your plot. And so if we actually plug this in for x into our equation, because of properties of cosine, right? If we shifted by this particular amount, we would just get the same function back. So this is sort of taking it a whole step further, so you can imagine actually physically shifting these functions, or we can imagine actually our transformation actually being plugging this into our function and realizing we're getting the same thing back, right? And again, this is just a property of cosine functions. So this is cool. So we can think about solutions to physical equations having certain symmetries, but that actually is not really going to be most important to me as a theoretical physicist. So the most important types of symmetries that I'll care about are symmetries of physical laws themselves. Right, so some waves, so this particular solution for a wave happens to have a certain symmetry. But there are other types of waves that would not have that particular symmetry. But instead we could think about a symmetry of the physical law itself, right? Not of the solution of the physical law, right? We were looking at the symmetry of the solution, not of the physical law itself. So let's look at a very introductory level example. So when you first take a physics class, either in high school or in college, one of the very first things you do is you study projectile motion. So you have some ball here, which you shoot up with some initial velocity, it flies, and it comes back down, right? We know that the physical law governing governing the motion of this object is F equals ma, right? This is Newton's law. And in particular, if we have gravity, that's gravity is pulling this ball back down as it falls, then Na equals mg, where g is 9.8, right? That's just the force of gravity on the ball pulling it back down. Now, hopefully, any good physics student would know if they wanted to solve for the path of this particle, the first thing they need to do is set up some coordinate axes. They need to say, if I'm measuring the position of this ball as it moves through space, I need to know where I am measuring it with respect to, right? And the easiest thing to do is generally to say, okay, I'm going to set my origin at the initial position of this ball, and then I'm going to measure its point at every point along the trajectory relative to this place that I'm calling 0. Right? So that's the very first thing we need to do if we want to write a function describing the solution. And if we did that, we would find that the function describing the path of this particle has an x coordinate and a y coordinate as a function of time, would just be described by this here, where this is some initial x velocity of the particle times time, and then g here is the gravitational constant, which is telling us how fast it's accelerating towards the Earth. So this would be the easy thing to do. Now, if you were feeling frisky one day and wanted to not make your life easy, instead you want to make your life hard, you could have instead put your origin over here and solved F equals NA. And you could do that, and you would just get more complicated answers. But really, right, the path of this particle is the same either way. You're just choosing to call 0 somewhere different. Right, so I've done some transformation here, where the transformation is, this is said to be a translation in space. We're translating our origin relative to our particle. The solution of the path of this particle is not symmetric under this translation. Because if I do this translation, you can look at the function up here and the functions down here. These look different. So you might want to say that the physical law governing the path of this particle is not symmetric under translations. But it turns out that it is. It's just this particular solution is not symmetric under translations. And one way we can think about this is the solutions look different, these functions look different, but the physical quantities that we would actually measure, like we don't actually care about these functions. What we care about is you can measure how high is the particle at this time. What is its range? How far did it go? Those questions are invariant under this choice of where we put our origin. This distance, where it started to where it ends, is the same in both cases. And so physical quantities, the things that we actually measure, are invariant under these translations. And so here I would say the physical law, which is F equals ma, governing the path of this particle is translation invariant, even though the solution is not translation invariant. Yes?
So the sphere rotating it, that invariance is the fact that the shape is described by a sphere, it's invariant
Yes.
to changing.
Yeah.
And we applied that, and it was sort of a natural way of thinking of it. It's invariant if I go by
Yeah.
90 degrees when it's a
Yeah.
cube.
Yeah.
And here you're saying here's a physical law,
Yeah.
and the physical law is invariant. It doesn't. The solutions of where the
Right.
thing goes is
Yeah.
always the same. It doesn't matter where you chose the origin.
Yeah. Well, so these functions, which we might say are solutions, are not invariant, but the physical quantities, the things we actually measure, the things we care about, those are invariant. Yeah. So this is the type of thing that I actually care about, which feels a little more abstract, right? I care about physical laws being invariant under certain symmetries. Okay, so now that we have an idea of what we mean by different types of symmetries, let's think about symmetry and special relativity and what Einstein did that made symmetry such a fundamental idea. So before Einstein, we had what is known as Galilean relativity. So Galilean relativity said the laws of physics take the same form in any inertial reference frame. So right away there are some words we need to define. So what is an inertial reference frame? So generally you can think of an inertial reference frame as being a non-accelerating reference frame. So if you're in like an airplane while it's taking off and you're accelerating upward, that is not an inertial reference frame because you're accelerating. Or even if you're just in your car, right? You accelerate forward and you feel pulled back against your chair, that is not an inertial frame. But once you're cruising at altitude in that airplane, or once your car is sort of driving smoothly in a straight line, those would be inertial reference frames. And so what we're going to care about are these inertial reference frames where either you're standing still or you're just sort of moving at some constant speed. So in Galilean relativity, it is said that the laws of physics need to take the same form in any of these reference frames. So if you apply Newton's laws, F equals ma, it should work just as well if I'm standing here or if I'm, in an airplane cruising at altitude, at a constant speed. And one way to see that is any experiment that I would do here on Earth, standing still, should also work cruising at altitude in my airplane moving at a constant speed. Right? So an experiment can be anything that you think of, like if I toss this ball up and I describe the motion of this ball when I'm just standing here. If I'm on an airplane, once it's cruising at altitude at a constant speed, that would be considered an inertial frame. You could toss the ball up on an airplane like this, and nothing weird would happen, right? On the other hand, when the airplane is taking off and you have this gigantic acceleration, if you toss the ball, it's going to, fall back, right? So experiments would look different, and therefore the laws we would need would look different in accelerating reference frames. So in Galilean relativity, it is said that the laws of physics are going to be the same in any of these constant velocity, constant speed reference frames. The other fundamental principle of Galilean relativity was probably not actually stated. It was an assumption that was sort of being made without even realize they were making this assumption because it feels so intuitive. So the second part of Galilean relativity is that the time between two events is the same for any two observers. So by two observers, it could be like a person just standing here and then a person, going by on a train or something. So they're in a different reference frame. So you could have two observers, one who's standing still, one who's moving at some constant speed. And the assumption being made, probably on accident, is that the time that the person standing still measures should be the same as the time that the person moving on the train measures. And that feels real intuitive. And that's why it probably wasn't even a stated assumption, because we're just like, of course the time is going to be the same for all observers. Like, why would it not? Why would it be anything different from that? So the first thing I want to point out is these are really symmetry principles. So these you might just think of as sort of some starting axioms, but they're really symmetry principles. And they're symmetry principles in that we're talking about the laws of physics. These are our object. Right? Again, when we talk about symmetries, we want to talk about the object and what transformation we're doing. So our object in this first one are the laws of physics, and they're invariant under transformations between different inertial frames. So moving between different inertial frames is the transformation that we're doing to our object, the laws of physics. So this is really we're stating that this is a symmetry of nature. And then this second sort of implied symmetry or secretly assumed symmetry is that the time between two events, now this is our object, is invariant under the transformation of moving between reference frames. So it turns out that there are certain implications that come from these symmetries. So for instance, we could consider a boost. So what is a boost? A boost is moving from a stationary reference frame to one of these moving reference frames, right? So a Galilean boost, we can write down a coordinate transformation, and I'm not going to go through the derivation because it's not necessary. But if we start by taking this coordinate transformation that you would use if you're going from being a stationary observer to a moving observer, from this you can derive the fact that the speed of light changes when you boost between different reference frames. Now let's look at a picture to help us think about this a little bit better. So if we're standing on the side of the road, and I'm calling this a loud frame, and a truck is going past to the right, and a car is moving past to the left, right? This is what we would see standing on the road. If we jump into the truck, it's going to look like the car is moving faster, right? Now we think we're stationary, and the car looks like it's moving even faster. We've hopefully all experienced this, right? So you can imagine this. Now in Galilean relativity, a photon, which is a particle of light shouldn't behave any different from other objects. So if I represent light, a particle of light by this little dot, then we would expect it to behave just like the car. And we would expect, if we're standing here on Earth and we see, so C is the letter used to represent the speed of light generally. So if standing on Earth, we see the speed of this particle of light as being C, then we would expect if we jump into this train, just like with the car, this particle of light should look like it's moving faster, right? Just like the car did. And this feels very intuitive with our everyday experience. However, in the late 1800s, Michelson and Morley did an experiment to test this. Well, they were testing for something known as the ether, but what they found was that the speed of light, and this is really the speed of light in a vacuum, is the same in all reference frames. So which contradicts what we just saw. So what do I mean by that? So what they found is that if you're standing on the side of the road watching the truck and then watching a particle of light, and you see this particle of light moves with this particular speed, what they found is that if you jump in this truck, this particle still moves with that same speed. It doesn't matter. So, and we could jump in a rocket ship that's moving super fast to the right, and still we should measure the speed of this light particle as being some constant. And so what it turned out is that the symmetry principles, remember there were two symmetry principles of Galilean relativity. The laws of physics take the same form in inertial reference frames, and that the time measured between events is the same in all inertial reference frames. Instead, it turns out that second one is false, and what we really need to enforce as our second symmetry, so this is the same as before, is the fact that the speed of light in a vacuum is the same in any inertial reference frame. So this is a new symmetry principle. And this symmetry principle was explicitly enforced when deriving what is now known as special relativity. So and again, these are really symmetry principles. The first, the same as before. And the second, now we would say the speed of light in a vacuum is invariant under transformations between inertial reference frames. So Einstein decided to take these two symmetry principles and make them fundamental to his new way of describing mechanics, which is special relativity. Now, there's a different name of the group of symmetries that he uses, which is known as the Poincaré group. Has anyone heard of the Poincaré group before? Anyone? The other faculty members? All right, but this is fun, so I'm going to tell you. So symmetries, the mathematics of symmetries are the mathematics of group theory. And so there's something known as the Poincaré group, which is the set of symmetries of special relativity. So there are, 3 or 4, depending on how you want to count. These are the set of symmetries. So what are they? Space and time translations. So Einstein said that the laws of physics should be symmetric under translating in space. So translating in space is just like moving side to side, up to down. Those are translations in space. But also translations in time, right? So the laws of physics should not change tomorrow as opposed to today. So changing from instant to instant, the laws of physics should stay the same. So this again should be quite familiar, or this should be not surprising, I guess. Spatial rotations, so like rotating the sphere, right? So if we rotate our whole experiment, then we expect the outcome to be invariant under that. And then boosts are these transformations when we move to a moving reference frame. So if we jump on a train that's moving at a constant speed, the laws of physics should take the same form. So this is the set of symmetries that Einstein enforces in his theory of special relativity. So now, again, we can think about boosts, which again is moving to that, or translating to that moving reference frame. Now, the coordinate transformations look a lot messier. I don't know if you remember what the functions looked like before, but they were nice, simple things where time was the same. So it was t prime equals t. Now these look like some messy things. But it turns out that from these, you can find the fact that the speed of light will be invariant under these coordinate transformations, which is what we wanted, right? Because Michelson and Morley taught us that the speed of light should be invariant. So Einstein made this big change, and actually historians of science debate whether Einstein was really inspired by this Michelson-Morley experiment or whether he just developed his theory of special relativity independently. But regardless, right, he did this thing that changed our fundamental assumptions, and it fit with this new experiment, which said that the speed of light is the same in all reference frames. But did he break other physics while doing it? You're like, okay, well now it matches with this one experiment, but this is some weird stuff you're doing. You're telling me, you know, you're losing the assumption that time is the same for all observers. Have we broken physics? So it turns out that starting with these symmetries, we can derive new physical phenomena. And if you do that in special relativity, there are two sort of famous phenomenon that we could talk about. So the first is known as time dilation, which says that time passes differently for different observers. So has anyone seen the movie Interstellar? Anyone see that? So you guys remember, like the guy right outside the black hole, time passed very differently for him, like a different amount of time passed. Right, so that's a real thing. Like that's not just like sci-fi. Interstellar is actually a very scientifically accurate film. And that really is this effect right here. Right? So it's a little more general because you need general relativity instead of special relativity to understand Interstellar, but it's the same sort of basic idea that time passes differently for different observers. And this really comes from just enforcing this different set of symmetries. It turns out that length is also measured differently for different observers. So if I have, where's that meter stick? Thank you. So if I have this meter stick, right now it's a meter, the meter stick, right? If I measure something relative to this meter stick when I'm standing still, that's cool. You know, I can measure the length of this marker. But now, if the marker sits here and I run past the meter stick super fast, I am going to literally measure this marker to be a different length. And this is not like a, optical illusion or something. If I am running past this marker, I will measure this marker to be a different length. And this again really just comes, or can be derived, from enforcing these different symmetry principles. And so the difference in symmetry really led to very different physics, right? And these effects are very tiny at everyday speeds. And that's why people before Einstein didn't know, right? Because to experimental accuracy, at Newton's day, they would have never been able to measure time dilation effects, right? No one hung out right outside a black hole in Newton's day, right? But now, experimental technology has allowed us to test things like time dilation, and in fact, by just putting measure the fact that that clock ticks off a different amount of time than a clock sitting on her. So this is not like sci-fi. This is like experimentally verified physics. All right, we are way behind schedule. So we'll talk a little bit about classical mechanics next. So Noether really is the next major player in this film of transforming the way we think about symmetry. So she was a German mathematician. A little bit about her. She's an impressive person because in her day, women were not mathematicians, right? Unfortunately. But she fought her way to becoming a professor at an institution in Germany. So she actually, beat the odds and was able to do that. Only for Hitler to come to power, and she actually was Jewish and then ended up having to flee the country. But then, happy end, she came actually to the United States and ended up, things still worked out pretty well for her. But I always thought that was a little sad. She fought her way to this academic position, beating all odds as a female mathematician in her time, only for the fact that she was Jewish for her to have to leave the country. But impressive lady. So she taught us that for every continuous symmetry, there is a conserved quantity. And vice versa. For every conserved quantity, there must be some continuous symmetry. So again, this word continuous is important. So remember I said to remember the difference. This was the difference between a sphere can be rotated by any amount, whereas a cube can only be rotated by discrete amounts for it to be a symmetry. So for every continuous symmetry, there is a conserved quantity. So most of you probably learned about conserved quantities. Again, if you've taken 114, you have. So for instance, you learned that momentum is a conserved quantity. So it turns out the reason momentum is conserved is because of spatial translation of your system. So invariance under spatial translations leads to momentum conservation. So you were probably just told momentum is conserved. That's just the way it is. If we think about symmetries as being a fundamental thing, spatial translations are the reasons we have momentum conservation. Similarly, energy is conserved. This is because of time translation. So because the laws of physics today are the same as they will be tomorrow, this is why the total amount of energy that we would have in an isolated system is the same today as it will be tomorrow. Similarly, angular momentum is a conserved quantity. This is due to rotational symmetry of your system. So I think I'm going to skip a couple things to get through everything. So, who's taking analytical mechanics next semester? Anyone? One? No one else? Two? All right, so next semester we will learn about this slide, which I'm not going to talk about today. So, in classical mechanics, you learn that the Lagrangian is a function that describes your system, and symmetries of this Lagrangian are going to lead to conservation laws of your system. So, it's a bunch of math, so you're going to be so glad that we're skipping all of this right now. All right. So I won't talk too much about this, but I want to point out, so what I want to say, right, so if momentum is conserved because of spatial translations, can we think about systems where momentum is not going to be conserved? And it turns out, and I won't go through this derivation, I don't know why I included all this math. Anyway, see me after if you want to talk about the math behind this. So it turns out, so what is a harmonic oscillator? So harmonic oscillators are very important in every field of physics, because it turns out that lots of things in nature can be described as harmonic oscillators. So in particle physics, for instance, we think about expansions as little tiny harmonic oscillators. So an example of a harmonic oscillator, so this guy So what I want to ask you is the momentum, so if we want to think about the momentum of just this cart, is the momentum of the cart conserved in time? So momentum is mass times velocity. Is the mass times velocity of this cart staying constant in time, or is it changing? It's changing, right? And why is that? That's because by attaching the cart to this spring, I have broken the translational invariance of this cart, right? So what the cart experiences is different when the spring is compressed versus when the spring is stretched. So by attaching it to this spring, or applying this external force, right, I have broken the translational symmetry. So in this example, you could see mathematically why that's true. So Noether's theorem, in summary, taught us that symmetries are the reason we have conservation laws. So by breaking a symmetry, by attaching this spring, momentum is no longer conserved, right? Whereas if I have the cart free and I just pushed it and didn't have anything breaking the translation symmetry, then the cart, momentum of the cart, would be conserved in time. All right, so I wanted to get to, oh my goodness, I planned way too much for this talk. Sorry, guys. I wanted to talk a little bit about symmetry and quantum mechanics. So in quantum mechanics, we specify a system by starting with its Hamiltonian. And just like in classical mechanics, it'll turn out that symmetries of this Hamiltonian, which describes our system, will lead to conservation laws. And again, I'm not going to go through all of that. So again, continuous symmetries in quantum mechanics are going to lead to conserved quantities. So in that regard, quantum mechanics is not going to be very different from classical mechanics. Continuous symmetries, so things like momentum, right, can be conserved if you have spatial translation invariance of your system. But what about discrete symmetries? So we said at the beginning there are two classes of symmetries, continuous and discrete. Continuous symmetries lead to conserved quantities. Can discrete symmetries do anything? So in quantum mechanics, the basic object that you study is known as the wave function, and this describes the state of your particle. Now, who is in quantum mechanics right now? No one? Who has taken quantum mechanics? Oh my goodness, friends. So, it turns out this wave function, which is a function describing the state of your particle, is never measured directly. So we have a function, instead we only measure the square of this function, which right now you're like, okay, who cares? So let's consider a two-state particle, or a two identical particle state. So let's say we have two electrons right here. We can describe this state by this thing called the wave function, which tells us, so this is the position of particle 1, this is the position of particle 2, and maybe they're moving around in time. So this is just a function you can just think of that's describing the way these particles are moving quantum mechanically, right? But again, the thing we measure is never this wave function directly, instead it is the wave function squared. Now what happens if we exchange these two particles? Now I told you they're identical. They're identical particles. So you would expect anything that we measure when we exchange these two particles should be the same, right? They're identical particles and I've just changed the position of these two particles. So the thing that we measure, again, is this amplitude, not this wave function itself. And so if we have the function with particle 1 here and particle 2 here, and we switch their locations, we expect these things to be equal. right? Because this is the physical thing we're measuring about this system. This is the physical thing we're measuring about this system. But these particles are identical. These things should look the same. Now, if we take the square root of both sides, so if you're careful when you take square roots, you remember that you have to pick up a plus or minus sign, right? When you take the square root of x squared, it's not x, it's plus or minus x, right? And so we find out that there are two types of particles in nature, actually. Ones where you get a plus sign and ones where you get a minus sign. And these are said to be so, these end up being two distinct classes of particles. Those that are symmetric, which is when you get the plus sign, and those that are anti-symmetric. So this is like an even function, odd function type thing here, right? So those that are symmetric and those that are anti-symmetric. And these particles have names called bosons and fermions. So bosons are things like the photon, which is the particle of light, the Higgs boson, which maybe you heard about in the news in like 2011, I think they discovered the Higgs boson, and the gluon, which helps hold the nucleus together. So these particles have this plus sign, or electrons, right? Electrons orbit around in atoms. Quarks are actually what make up protons and neutrons, or neutrinos, right? So it turns out that this symmetry or anti-symmetry property determines which class of particles we have. And Tom is standing almost out of time, because I had decided I wanted to talk about way too much. So the point being, sorry. So the point being, if we look at, so this is known as the standard model of particle physics. So some of these particles, again, should be familiar. So this is like the periodic table for physicists, right? So most of you have learned about the periodic table, right? That's where we have all of our elements. Physicists have something called the standard model, which is how we classify all of our particles. And it turns out all of these particles on the left are classified by this anti-symmetry property, and all of the particles on the right are classified by the symmetry property. Okay. So, sorry, I keep forgetting that makes me go away. All right. So in quantum mechanics, symmetries not only lead to conservation laws, but applying these discrete types of symmetries helped lead to the discovery of really different types of particles and different classifications of particles. Okay, so just in the last couple minutes, a few words about advanced symmetries. So, has anyone heard of supersymmetry before? Two people? Maybe. Again, is it this little corner right here? So supersymmetry is really cool. So supersymmetry is a conjectured symmetry of our universe that probably isn't real, or so far we don't have evidence of. But in supersymmetry, what scientists do is you assume you have, so down here are all of our normal standard model particles that we were just talking about. So you see the electron, the Higgs boson. So in supersymmetry, there is a partner of every standard model particle. So for the electron, it has what's known as a supersymmetric partner called the selectron, which is a silly name. The quark has a partner called the squark, which is also a silly name. You'll notice this is what the physicists did. They thought, oh, we need a partner for all of the normal particles. Let's just add an S to the beginning. And that'll be the supersymmetric. So not all of them are just adding an S. But we have the gluon has a gluino, which is pretty cute. The Higgs is a Higgsino. And so in supersymmetry, what they did is they enforced a different set of symmetries which led to the fact that we would expect to have an entire new set of particles of nature. Now, everyone was very excited when they first turned on the Large Hadron Collider because they thought they were going to find all of these particles. But then they didn't find all of these particles, and maybe that's why no one raised their hand when I said who's heard of supersymmetry. But a lot of people today still think about supersymmetry because there are ways to break symmetries. And so it's possible that this is true only at very high energies, and that at everyday energies this symmetry is broken. All right, so I think I'll just stop there instead of talking about more. So really, in summary, I only had one bullet point, which is that symmetry is important. And really that in modern theoretical physics, what we do is we see symmetries not as useful, but fundamental. And they're the starting point from which physical